to solve a Leetcode problem 2179 called Good Triplets in an array. So we are having two arrays, nums1 and nums2. We want to find the total number of good triplets. So the good triplets means the sequence are the same. For example, we have a number like let's check one by one. So we have like four triplets, 2, 0, 1. The first one is 2, 0, 1 for nums1. Yeah, so the sequence is 2, 0, 1. But for the second one inside nums, we cannot find the sequence of 2, 0, 1 because it goes back, it's not forward. Yeah, actually there's only one triplet meet the condition of good triplets. So for 0, 1, 3, 0, 1, 3 inside nums1, it is a sequence. Yeah, I mean the sequence, not the numbers 0 less than 1 less than 3. I mean the positions of 0 less than positions of 1 less than positions of 3 in nums1. And we can also check in nums2. The position also the same. So the position of 0 less than position of 1 less than position of 3. So there's only one good triplet. How should we solve such problems? Actually, this is a really difficult problem. First of all, we cannot find, how can we turn this problem into easier data structure? Actually, the data structure is also difficult. It is a binary index tree. Yeah, and also it's really difficult to transform this problem into binary index tree. So I will solve this problem using binary index tree. And first of all, I will explain a little bit about my binary index tree template. After that, I will talk about how we can turn this problem into a binary index tree. Yeah. So first, let's go to the whiteboard. Yeah, so for my binary index tree, I will start with index 1. Yeah, so a lot of problems for the binary index tree, they always start with index 1 because index 1 is easy for the bit manipulation. Because for binary index tree, basically inside the code, no matter we need to calculate the sum function, or we need to calculate the add for the binary index tree, or we need to innate the binary index tree. We always need the binary bit manipulation. So we need to use, for example, this is a bit, this is a number I. We basically need to use I and minus I. So this is called the low bit operation. Basically, we need the low bit operation. And when the Fenwick designed the binary index tree algorithm, he found this is easier for the calculation. So for the index, we're gonna always start as 1. Yeah, let's just check an example. So for example, we have a nums inside. This nums is just an array. Inside the nums from index, we're gonna prepare the first one as index 1 because, as I explained, this way is easy for the bit manipulation. So the index 1 will be 5, and then index 2 will be number 2, and here index 3 will be 9, and index 4 will be minus 3, and this is gonna be 5 and 20 for index 3, and 7 and 8. It will be like this. Now we're gonna have the binary representation of the index. So it's gonna be 0, 0, 1 until 1, 0, 0 for each of the index. Yeah. And for the binary index tree operation, so for the first index, so index 1, if we find this bit, so we're gonna find the first bit. If it is 1, we only check the first bit from the right to the left side. If it is 1, we set it as our current number. It is 5. Yeah, so the current number is 5. So when it comes to 0, so when this low bit, so we call this bit is low bit. So when the low bit, when the lowest bit or the least bit becomes 0, we're gonna use the bit manipulation for the innate preparation for the binary index tree. We're gonna plus this 5. Yeah, so actually this number 2 is the parent of number 5. So if it is a parent, we're gonna plus this number. So this 2 would plus 5. So here gonna become a 7. Yeah, so for this number, basically for the first number it is itself, but for the second number it's gonna plus this first number. And similarly for others, so this 9 we're gonna keep it as 9. And for this number, last number, we're gonna keep it plus this number. So 9, yeah, and when it comes to this number is 9, yeah. But when it comes to this number, yeah, it is not 6, because 9 plus minus 3, it is 6, but we need also to plus the number from this 7. So 7 plus 9 plus minus 3. So here we're gonna keep it 13. Yeah. So for the calculation, actually in this place it is just 4 numbers, and in this place it is 2 numbers. But as you can see, the index 3 it is only 1 number, it is 9. And also similarly for others. So for the index 5, so it's gonna be a 5, and for the index 6, it's gonna be 25. 5 plus 20, it is 25. And for index 7, it is just 10. Yeah. And here is just 1 number, here 2 numbers. Yeah, and here just 1 number. And here gonna be 4 numbers. So if it is 4 numbers, it is 20 plus 10 plus minus 7. Yeah, let's check. So here 5 and 20, here should be 25. Yeah, so 20 yeah, so here this number actually should be all those numbers, not from here. Yeah, so if it is index I is index 8, it's gonna be all of the numbers. So if here is 10, so it's gonna be start from yeah, let's check from 13 plus this number 13 would plus 25, it is 38, and plus 10 it is 48, and plus minus 7 if it is 41. Yeah, so this is basically for the preparation for the binary index array. So in my template I'm gonna prepare a tree array. So inside of the tree it is just a 1D array. So inside of the 1D array I'm gonna prepare these numbers like 5, 7, 9, 13, 5, 25, 10, 41. Why I gonna prepare this? Because this will be easier for the sum and add calculation. So for the sum calculation inside, it would be an index. If I use index, for example, 8, I got my result immediately, it is 41. So it means from index 1 to index 8, all those numbers plus all those numbers should be equal to 41. So I can get my result immediately if I use a sum of 8. Yeah. So it's gonna be 41. Actually, this sum or add, it is just log n time complexity. That is why it is so fast. Yeah, it is 41. So how can we calculate sum 7? Yeah, actually, for calculating the 7, so this is the binary representation of 7. It is 0, 1, 1, 1. So we're gonna first check the most significant set bit. Yeah, so yeah, let me try to explain like this way. Yeah, so for this operation we call it yeah, so we call it so for an add. Yeah, let me first explain the sum. So I call it minus the last set bit. Yeah, so this means minus the last set bit. So the last set bit from here, this is the last set bit. This is 1 is the first set bit, and this one at the last is, I call it last set bit. So I minus the last set bit or flip the last set bit. So this bit will become 0. So it means sum 7 should equal to array 7 plus, array 7 plus, and I will flip this bit, last set bit, so it will be 110. It means I gonna plus 6, and then I just change this bit to 0, change the second bit to 0, it's gonna be 4. So it means 7 plus 6 plus 4. Let's check the result. So 7 it is 10, and 6 it is 13, it is 23. Let's check 6. 6 is 25, 7 is 10. So 25 plus 10 and plus the index 4, 13. So it's gonna be, let's check. It's gonna be, this is 13 and 23 and 48. So it's gonna be 48. So we just need to find 3 places. But if we check the array from 0 to 7, we need to plus all those numbers. Let's check if the result is 48 or not. Because the total number is 41, we should know that 48 minus 7, it is 41. So it means 48 is right. So why we are calculating like this? Because it is also from the low bit operation. And this I and minus I actually is for the low bit operation. So for example, this is 7111, and after this operation, I gotta set it to 110, and after another low bit operation, it's gonna be 100. It's gonna be 4, and after another low bit operation, it's gonna be 0000. So I will jump out of the loop. So later on I will explain the code. Maybe you can connect a little bit about why I gonna use the template like that. So this is the sum operation, and also similarly for the add operation, we're gonna also use the low bit operation. So for the add, this add is just need to add a number. For example, let's add a number for index 4. So previously this is minus 3. So if we were to for example plus a number, for example we need to plus a number 5. This means just add a number 5. So here for this number currently it's gonna be 5 minus 3, it's gonna be 2. So currently this number gonna be 2. So for this add operation, I gonna check this one immediately. So for the nums array, it is 2, but it doesn't matter. Basically focus on the tree array. So this array, I call it a tree array. I call it T. So for this index 4, I gonna plus a number with 5. So here gonna be 18. And then I gonna use another bit operation. So I call, so we call it add last set bit. Add last set bit operation. So this add last set bit means this is 1 like here. So after the operation, this set bit will be 1 plus another 1. It's gonna become 1000. So this means my next position is at index 8. So from index 8, I need to plus this number. So which number I need to plus? I need to plus a number 5. So here 41 becomes 46. And then I need to add another set bit. So this one I gonna plus a 1, so it's gonna become 1000 and 0. So this is 16 because this is 1, others are 0. So it's gonna be 16. 16 is longer than my array because my array is only so my array, so the maximum index of my array is only 8. But currently my index is 16. It is more than my array, so I will go out of the loop. Yeah, so this is basically the AND and sum operation for the binary index tree. Yeah, and this is why it is log n time. Yeah. Now let me just go back to the question and why we can turn this question into the binary index tree problem. Yeah, and for this problem, basically we need to find the right sequence from nums1 and nums2. So for nums1, we're gonna copy these two numbers, yeah, to nums array. Yeah, so basically we have those two times arrays. We're gonna find the right sequence. But this is difficult to check because all the numbers are random. Yeah, because like 0, 1, 3 or 0, 1, 3, it can be any kind of sequence. But actually, the index is also from 0 to n minus 1, and the numbers is also from 0 to n minus 1. So this means we can use a map because it is one number to, yeah, because this 0 to this 0, this 1 to 1, it is a 1 to 1 map. Yeah. So for this kind of map, we can prepare the sequence of nums1 as 1 as 0, 1, 2, 3. If the sequence is like 0, 1, 2, 3, so we can use the binary index tree to do some operations. Yeah, so this is why we need to do some preparations. But how can we prepare the map? So we just need to map the number 2 with 0. Yeah, let's just map number 2 with 0. So for the first number, yeah, map it with the index 0. So we're gonna prepare a dictionary. 2 gonna map 0, and 0 gonna map 1, and 1 gonna map 2, and 3 gonna map 3. So for nums1, each of my numbers will map its index. We're gonna prepare such a map. So this map is prepared for preparation to turn this nums1 into a 0, 1, 2, 3. And then we're gonna similarly use the map to turn nums2 into a new sequence. So this sequence will be similar to 0, 1, 2, 3. Yeah. So this is some knowledge from the mathematics. So for example, if my sequence is 0, 1, I gonna have a map. So this 0 gonna map a 1, 1 will map a 2. So actually the sequence is gonna always be the same, 0, 1, 1, 2. Yeah, because here this 1 gonna represent 0, this 2 gonna represent 1. So the sequence will also be the same. So we can use this idea. If we find a number 0 inside nums2, we're gonna find the index. So the index is 1. So for nums2, we're gonna prepare a nums2, the first number 0 gonna be 1, the 1 gonna be 2, and the number 2 gonna be 0, and the number 3 gonna be 3. So this is the new map. So we're gonna turn nums1 and nums2 into the new sequence. So for nums1, it's gonna be 0, 1, 2, 3. So for nums2, it's gonna be 1, 2, 0, and 3. Yeah, and if we can turn something into this, we can check the result easily. For example, if we want to check, let's try to check number 1. Yeah, let's check the original number of nums1 and nums2. So for nums1, at the left side it is 0 and 2, and for this one at the left side is 0. So we find one number, it is 0. Yeah, and by the way, we are going to solve this problem, need to first find the numbers in the middle. Yeah, because it is a triplet. If we find a middle, it is basically easier for us to check. We just need to find a left number and find a right number at this side. Yeah, if we find the right sequence, we're gonna get one result. Yeah, if we try to use the first yeah, if we try to check the first number, it's gonna be really difficult. Yeah, so this is why we need to check the mid number, and then we're gonna find the number before it and the number after it. If they are the same, we're gonna count it as the result. So for this, for example, we're gonna check number 1. So at the left side for number 1, it is 0, 2. Yeah, and for the number 2, it is 0. So we find one number. Yeah, and now let's just check the new transformed array number 1 and number 2. So for this one, similarly, we're gonna check this number 1. So for this number 1, at the left side, it is 0. And here for this number, yeah, for number 1, yeah, for number 1, we find one number, but which number returned? Returned 1 to which number? Let's just check. Because we turned 1 to 2, yeah. Because for the map, we turned this 1 to 2. So now we are going to check this number 2. Yeah, as you can see for number 2, at the left side it is 0, 1, and for this 2 it is 1. Yeah, actually it's basically the same, just to change the numbers, but the sequence are totally the same. So we also find one number, it is 1. Yeah, we also find one number. So this means we can use the new array of number 1 and number 2 to check the result. But how should we check the result? Yeah, so for example, basically we just need to check the numbers in between. We don't need it. So for example, for number 2, inside number 2, we just need to check the numbers 2 and 0. Yeah, because 1 and 3 doesn't matter. Yeah, because for 1 and 3 at the left side there's no numbers, and for 3 at the right side there's no numbers. So we just need to check two numbers 2 and 0. Yeah, for the first number 2, we're gonna, yeah, so for the first number 2, yeah, let me put the, yeah, let me just put the numbers here, maybe easier to understand. Yeah, this is for number 1, and this is also for the binary index tree. We're gonna prepare like this. Actually, for the binary index tree, it's gonna start with index 1, but here for simplicity, we just yeah, use the example as index 0, because index 0 and 1 just need to, yeah, just need the actual calculation. It's gonna be easier to calculate. Yeah, so here we're gonna have like 0, 1, 2, 3 for number 1, and for number 2, similarly, I'm gonna put it here. So it's gonna be 1, 2, and 0, 3. Yeah, first of all, we're gonna check this number 2. So for this number 2, this is inside number 2. Yeah, after transformed, I'm gonna check the previous number before this 2. It is 1. Yeah, so for this 1, I'm gonna compare. I gonna find the position, because for the positions here, I just keep it similarly as 0, 1, 2, 3. Actually, this is the index and this is value. Yeah. But for the binary index tree, I will keep it as 1, 2, 3, and 4. Yeah, but here, let's check this 1. So for this number 1, I'm gonna first find the index with 1 and check the number. And inside the tree from the beginning, I'm gonna keep it always be 0. Yeah, this is the preparation for the binary index tree. So the t would be 0 from the beginning. Now I find a 1. For the number 2 at the left side, I find a 1. And for the number 1, I'm gonna find the index position, it is 1. So for the binary index tree add operation, I'm gonna add 1 from here. Yeah. Now I'm gonna calculate how many numbers at the left side of index 2. I just need to check inside the tree array. So for this number 2, I'm gonna check the left side. So this is the 2. Yeah, this is number 2. I'm gonna use this number 2 to find the index. It is a 2. Now at the left side there's a 1, so I gonna count it as 1. Yeah. So for this count array, I gonna count it. This I gonna count prefix. For the prefix array, it's gonna be 0, 1, and some numbers. And for the last, it's gonna be 0 because it's gonna be represent for the first number. It must be 0. For the last number, it must be 0. Now let's check the nums2. So for the nums2, yeah. So for the nums2, I gonna array. I gonna check the next number. It's gonna be 0. So the number before it, it's gonna be nums2. So for nums2, I find the index 2. I gonna plus a 1, and then I gonna check this 0. Yeah. This 0, I gonna check this index 0. From the index 0, I gonna check from the left side. So from the left side, there's nothing. Actually, for the binary index tree, it's gonna have a 0. Yeah, so it is a 0. So this means here gonna be 0. Why? Because for the binary index tree, actually it is like 0, 1, 2, 3, 4. Yeah. And this is my nums array from 0, 1, 2, 3. Yeah. This is why this problem is really difficult, because we need to be very familiar with the binary index tree. And so for here, this is a 0 from the left side. We are sure for the binary index tree, this is the index 1 from the left side. It is the result is 0. So this is the prefix array after calculate. Listen, yeah, it is a 0, 1, and 0, 0. Now, similarly, we're gonna prepare a suffix array. So this is a prefix array. This is a suffix array. So similarly, for the suffix array, the first number and the last number will always be 0. And we're gonna first check this number 0 first. Yeah. So for this number 0, at the right side, it is 3. Yeah. But for the suffix, let's just delete. Just to remove the nums array, because for the suffix, I'm gonna prepare a new array. Inside, it's gonna be the same. Yeah. So inside, it's gonna still be 0 and 0 and 0. And for this number 0, I'm gonna check the number 3, because 3 is at its right side. So for the 3, I'm gonna plus a 1, and then I'm gonna check the index 0. I'm gonna find the index 0. It is here and then I'm gonna check at the right side. At the right side, there's only 1, so I'm gonna put it as 1 from here. Yeah. Now I go to the next number. It's gonna be 1. Yeah, it's gonna be 2. So first I gonna check 0 and check 3. Now I comes to nums 2 and check 0. Yeah. So for 0, I gonna plus 1 and find the index 0, and from this position I gonna plus 1. This 0 becomes 1. Yeah. Now I gonna check this nums 0. So at the right side, so first of all, I find first of all, I find the index 2, because currently my number is 2. So for this number 2, I find the index 2, and it's right, and then I go to the right side. So from the right side, there's only 1. So I will count it as 1. I put it here. Yeah. So after that, I gonna just multiply these numbers. So 0 times 0, it's 0. 1 times 1, it is 1. And this 0 times 1, it is 0. So finally, it is 1 plus 0. Yeah, because these ones will always be 0. These ones will always be 0. So in between, it is 1 plus 0. It is 1. So this is why we have the result like this. Yeah, so this is why for the first example, for my result, I printed out the prefix and suffix. It is 0100 and 0110, and then I'm gonna multiply those numbers. 1 times 1, 0 times 1. So the result would be 1. Yeah. Now let me just explain a little bit about the code. I think I focused on explaining actually I focused on explaining the method because the method is even more important than the code. Yeah, and it's even difficult to understand the method. After understand the method, maybe easier to understand the code. Yeah, now let me just explain the code a little bit. Yeah, basically this is the binary index tree template I prepared and I explained. Basically, I have three operations. Basically, this is the init. So the init is a preparation for a tree array. So for the self.tree array, I gonna plus a 0 with nums. So this 0 did not do anything because for my binary index tree, I gonna start with index 1. So I gonna prepare a padding of 0. Now I use a for loop to put the numbers inside the self.tree. Actually, it will be like this. Let me go to the whiteboard. Yeah. Yeah, actually it's gonna be like this. If we have a nums array after the init operation, the final result of self.tree would be like this, 579. And the calculation is basically from here. Yeah, and the calculation is from here. First of all, I prepare a 0 because the index will start as 1, and then I gonna use a for loop. Similarly, because my index start with 1, so I will use 1 to less of my self.tree. Yeah, this is an array. And the first operation, this is the core operation of the algorithm. I need to plus the current node to my parent. So the current node is my index. So my index should plus a low bit. So the low bit operation is I add -1. So after I use the low bit operation, I set it as my parent. So if the parent is less than the length of the array, if it is more than array, I don't need to do anything. Because it's out of the range. If it is less than, I gonna put the value to the parent. So self.tree p parent should plus equal to self.tree I. Let me just give you an example of this operation. Maybe easy to understand why we're gonna use this operation. First, let's just try to plus the first two numbers, 5 and 2. So how should we calculate? So for 5, it is index 1. Index 1 for the binary representation, it is 1 1 0 0 0 1, and for the index 2, the binary the -1, because of it is basically I plus I and minus I. So for the first index, it is 1 plus. Now let's do the operation I and -1. So this is the 2's complement operation. So for this number, 2's complement is 1 1 1 and 0 and plus 1. It is 1 1 1 1 and 0 0 1. So the final result would still be 0 0 1. I hope you understand that. So actually 1 plus 1 would be equal to 2. So this means my parent equals to 2. So this is my parent 2. So 2 should plus which number? Should plus nums I. So nums I is 5. So 2 plus 5, it is 7. So this is why we use the init operation like that. So this is why I plus I and minus I, this is the parent. And then for my parent, I'm gonna plus this number. Why we are doing such operations? Because this is for saving the time. And this is a preparation. While we are doing this, you think this is not important. We just get a 5. Actually, this operation, we put something for the next number, we get it a 7. And for all other numbers, it is prepared like that. After that, we're gonna prepare a perfect binary tree array. And we're gonna use this array to do the AND and SUM operations. Now let's try to check the add. The add operation is just needed to check the index. So if the index is less than the length of the array self.tree, so we're gonna do the beta operation. So the I would plus equal to I and minus I. This is the add the low bit operation. So the add last set bit. So finally, this set bit will be more than the length of the tree. Yeah, let me go back to the whiteboard to remind you a little bit about our calculation previously. So previously, I think we are calculating at index 4 with plus of 5. For the next one, we use the operation, it's gonna be 8. Yeah, actually, this is also the same. I will not do this operation. You can try the operation by yourself. Because it does takes more time. The video will be very, very long to finish. Yeah. So this is just called add the last set bit operation. So after add the last set bit, the number will be bigger and bigger until it out of the loop. I will just stop it. And this sum operation is just sum from the index 1 to index I. And this index I gonna be smaller and smaller because here is I minus equal to I low bit operation. So minus the last set bit. Yeah, so the last set bit, if it is 1, I call it a set bit. So the set bit will become 0. So the number will be smaller and smaller until I go out of the loop and then return the result. And this is from index 1 to index I. Yeah. Now let's go to the hard part about the make code. So for the make code, actually here is easier. We just prepare n equal to the length. And here for bit 1 and bit 2, this is the preparation, as I explained earlier, just prepared as a 0 inside each of the self.tree array. Yeah, inside the self.tree array. If we put it inside, basically we're gonna do all those preparations. Yeah. While we are doing an add or sum, we are doing the operations. While in it, we're gonna put the 0 inside and then do those operations. But the 0 inside actually we do some more calculations, but it doesn't matter. It didn't take so much time. It is just on. It is just a on time. And here for this operation, we just use n log n. Yeah, n log n time for preparations to put it inside. Yeah, actually you can also do something. Yeah, without preparation like this, maybe saving the time. But I think basically it's okay. Yeah, because this is just a template. I cannot change this template for my make code, so I would keep it like this. Yeah, now this is my map, as I explained earlier. I just need to map the value to the index. So this means my nums1 will become 0, 1, 2, 3 like that. And similarly, for nums2, I just need to use this map D with the nums2 I minus 1. So this for loop is just like the example from 1 to n minus 1. Yeah, because the index normally from 0 to n minus 1. And here it is 1 to n minus 2 because we don't need to consider the borders, the left border and the right border. So we just need to take the middle of all those indices. And then inside, we're gonna add the number before it. So for nums2I, it is this number. So but before it, it is num2 I minus 1. And then we're gonna use this map D. So after using the map, we find the index. And plus 1, this is just for the binary, for the BIT, binary index tree operation, because for the binary index tree, it is started with index 1. So this is why finally, after we find the index, for example, it is 0, we're going to plus a 1. We will see it as index 1. And this is the add operation. We just need to add a number by 1. And after that, we're going to calculate the sum. Yeah, so the bit sum from the left side. So this is the nums. Yeah, so for my I, current number is current number is nums I. Yeah, but I need to find the numbers before. I need to find the but for the sum of the numbers, basically I need to use the nums 2I. Nums 2I, because for the beta binary tree index tree operation, it should be nums 2I plus 1. But I need to get the number before it, so I need to minus 1. This is why it is d nums 2I. And then I just put the numbers s inside my index I. And similarly, this is for the suffix operation. So for the suffix, just need to check the index from the right to the left. So it is n minus 2 with 0. So this means from n minus 2 to index 1. And similarly, I do the similar operation. This is I minus 1, and here, so I'm going to use I plus 1. And this is going to be the same. And here, because it is from the right side, so I need to get the total numbers. This is I used beta 2 dot sum n. This means all the numbers, and then minus my current number. So it's gonna still be the same, d nums 2I, plus 1. So this d nums 2I is so for example, my current number is I. But from the right side, actually for the index nums 2I should plus 1. But actually I need to include this number, so I need to minus 1. So it is d nums 2I. And then I got all the numbers at the right side. And similarly, it's here suffix I equal to s. It's the same. Now I just need to check all the prefix and suffix and put them together, and this result plus its number times its number inside prefix and suffix, and get the result. Now let me submit it to check if it works. As you can see, it works. Now let me submit it to just prove that it can pass for all the testing cases. As you can see, it passed, even though it is slower. But I think after you learn the basic code, you can optimize to let it goes faster. But basically for the binary index tree, it's gonna be really slow. Thank you.